Hello and welcome to the Screencast. In this video, we're going to look at how we can use logarithms to answer a modeling question that involves an exponential function in a more realistic way. So back in activity 313, we saw the situation. The value of an automobile is depreciating. When the car is 3 years old, its value is $12,500. When the car is 7 years old, its value is $6,500. The car's value, t years after its purchase, is given by the function v sub 1 of t equals ab to the t, where v sub 1 of t equals this exact function. And then we also could say v sub 1 of t is approximately this function, 20,413 times 0.84918 raised to the t. And I just want to remind you that in this case, because time was being measured in years and we have this base b, that this base b equals 1 plus r, where r was the yearly decay rate. Again, that's because we were measuring time in years. So now we're going to look at the same situation, but we're going to model it instead using this model, v sub 1 of t equals ae to the negative kt. And as we've seen previously, if we're using this form, ae to the negative kt, then that kv value is the continuous decay rate. Okay, so we are going to set up this problem similarly to what we did back in activity 313. So we will have ae to the negative 3k. So we're substituting 3 in for t. So at 3 years, the car is $12,500. And then we can substitute 7 in for t, ae to the negative 7k. So we're substituting 7 in for t, if I said that wrong earlier, excuse me. And at 7 years, the value of the car is $6,500. And we know that the ratio of outputs in equally spaced inputs should be constant. So in other words, we should be able to divide ae to the negative 3k by ae to the negative 7k, and that should equal 12,500 divided by 6,500 in this exponential model. So simplifying this was going to give us e to the 4k equals, and then I'm going to reduce this fraction. You can check my work if you want, 25 over 13. And we can use logarithms to reverse this exponential function. So we'll end up with the natural log of 25 over 13 equals 4k. And then dividing by 4, k equals exactly the natural log of 25 over 13 divided by 4. And maybe for possible reference later, that is approximately 0.16348. Don't take my word for that. I would double check that you can actually put that into your computational device and also get that same decimal approximation. Don't take for granted that you can enter that incorrectly. All right, so we have our continuous decay rate, K. And now we're going to find our A value. And so I'm going to use the first equation. Could have used the second as well, but I'm going to choose the first. So if I want to solve for A, I'm going to divide both sides by e to the negative 3k. And so the exact value of A would be 12,500 divided by e to the negative 3 times the natural log of 25 over 13 divided by 4. And then that is approximately 20,413. Again, I would double check that you can actually enter that in your computational device and get the same value. So keep in mind when we have this format, AE to the negative KT, this A value that we just found is the initial value of the automobile. So interestingly, we have the same initial value whether we used the form AB to the T or AE to the negative KT. Right? And these are both models are modeling the same situation, so that might not be too surprising. And it kind of leads to part B. How does the value of e to the negative k in v sub 2, sorry, I should have called this one v sub 2 earlier because it was our second model. How does that compare to the value of b in v sub 1? So keep in mind, in v sub 1, our b value was approximately 0.84918. And remember, that was related to the yearly decay rate. And so we're wondering, how does that compare to e to the negative k? Well, we know that e to the negative k equals e to the negative, and then what was k again? Natural log of 25 over 13 divided by 4. And if we use our computational device, we see that that is approximately 0.84918. So what we're seeing is that e to the negative k is equal to b when we have these two forms, ae to the negative kt and ab to the t. So these two models, we're modeling the same situation. If we divide both sides by a, we have e to the negative kt equals b to the t. And if we manipulate the left side a little bit using exponent rules, we know that e to the negative k raised to the t, we would multiply those powers together. So we would get what we had up above, but that has to equal b to the t. And since both of these quantities, e to the negative k and b, are being raised to the t, and both sides of those equations are equal, we're seeing that, yeah, it does. It makes sense. E to the negative k should equal b. So it's kind of interesting there. We're going to look at one more thing. So we still have the same car. 3 years old, $12,500, 7 years old, $6,500. But now we're going to suppose that rather than having the car's value decay all the way to 0, the lowest dollar amount it ever reaches is $300. So explain why a model of the form v sub 3 of t equals ae to the negative kt plus c is more appropriate. So if we're told that the car's lowest dollar amount its value ever approaches is $300, we're really being told that the value of the car tends towards 300 as t increases without bound. And we know from our previous study of exponential functions and transformations that this model, v sub 3, is going to tend towards the value of c as t increases without bound. So we ultimately know that c has to equal 300, and that's because the car is going to approach a value of $300, whereas previously if we were only looking at, if we were only looking at the model ae to the negative kt, that model approached 0 as time went on. So we can use this transformed model to account for the fact that the car's value approaches $300. So lastly, predict how the values of A and K in the model V sub 2 of t, which is what we saw on the previous page, will compare to the values of A and K in the model V sub 3 of t. And then check your prediction by determining the values of A and K in the model V sub 3 of t. So pause the video, seriously consider how you think the values of A and K might change, and then we will check together. Okay, so whatever prediction you made, let's see what actually turns out to be the case here. So we know that if we let t equal 3, ae to the negative 3k plus 300 would equal 12,500. And we know ae to the negative 7k plus 300. So at 7 years, the value is 6,500. I'm going to divide or subtract, 300 from both sides of both of these equations. So ae to the negative 3k equals 12,200. ae to the negative 7k equals 6,200. We know that we can take the ratio of these equations. So we're going to have e to the 4k, right? If I divide this side, is going to equal 122 over 62, if I simplify it just a little bit. And then using natural log to reverse this exponential function, the natural log of 122 over 62 equals 4k. Divide by 4, so k equals exactly the natural log of 122 over 62 divided by 4, which is approximately 0.16922. And again, that is a continuous rate. And once we have our k value, we can go ahead and find our a value. So I'll use the first equation again. First, subtract 300 from both sides. So ae to the negative 3k equals 12,200. And then if we divide both sides by e to the negative 3k, we'll get our exact value for a. So a is exactly 12,200 divided by e to the negative 3 times the quantity, natural log, of 122 divided by 62. That's all divided by 4. That's all supposed to be in the exponent. And that is going to be approximately 20,269. And that would be the initial value of the car. So I would take a moment and compare these values we found for A and K in this model where we had a horizontal asymptote or a vertical shift of $300. Compare that to the values we found when we did not have that vertical shift, and think about why those values might be different.